So we're going to start out in Chapter 1, Section 3 on complex numbers. And our first objective is going to just look at the basic concept of complex numbers and their definitions. Now you should have encountered this in intermediate algebra at the very end. So complex number is written as the sum of a real number a and a multiple b, which is also a real number, of the imaginary unit I. So it looks like a plus bi. So the imaginary unit I, what is that? It has the property such that I squared is equal to minus 1. That's by definition. So just some history of this. Mathematicians literally just created this number, and they created the number because it has a property that they wanted. And that property was that if I square it, I get minus 1. No real number has that property. Every real number squared is either greater than or equal to 0. And this is not a real number. It's the imaginary unit, and it has the property that I squared is equal to minus 1. It's easy to argue that this was one of the greatest advances in mathematics. But just like many things in mathematics, when it was first introduced, people were really a bit tentative about it. They didn't feel quite right about introducing something purely by their own mental definition. But we literally couldn't do anything mathematically without the concept of complex numbers. They're everywhere. If there's any of you who are going into electrical engineering, you will find that that's used all the time. At any rate, for this reason, we're talking about the imaginary unit again, is referred to as the principal square root of 1. In other words, an equivalent definition is that I is equal to the square root of minus 1. Either of these definitions are fine. That definition or that definition here. They're equivalent. So now we're going to introduce a theorem. And we're just going to pretend, I don't have to do this, but let's, for the sake of argument, pretend that a is a positive number so that minus a is a negative number. So the square root of minus a is equal to the square root of a times minus 1, which is equal to a times I squared. Why? Because minus 1 is equal to I squared. Well, I can take the square root of I squared and just get I. In other words, since this is something squared, I can remove it out from underneath the radical sign, and that's what I do right here. But the square root of a still remains, and instead of writing it the square root of a times I, we write it I times the square root of a. So all of this middle part right here is just the steps I get. And we're now perfectly justified, since we've seen the steps, to start out, if I'm given the square root of minus a, and a is positive, then we can immediately write that's equal to I times the square root of a. Now if a is a negative number, then we don't need this, because minus a negative is a positive. And we could still use the rule, but it would be we'd still get the same exact result by doing extra work, and there's no reason to do that. So let's actually solve these, or actually simplify these three expressions involving the square root of minus a. Maybe I'll just use the mouse to do this stuff rather than my pen. I'll get it eventually. So let's do 1a. So the square root of minus 16. By our above rule, that's I times the square root of 16. But the square root of 16 is 4. Because remember, we're talking about the principal square root. And we write it not I times 4, although that's technically correct. We write it as 4 times I. I'm sure MATLAB would have a fit if you did it I times 4. So I don't need to do that. Let's just do 1b. So let's do the square root of minus 70. Well, again, by the rule, that's I times the square root of 70. Can I simplify the square root of 70? Well, let's try it. 70 is equal to 10 times 7. And 10 is equal to 2 times 5. So 70 is equal to 2 times 5 times 7. None of these are squared, so this can't be further simplified. We're done. It's just I times the square root of 7. And let's do C. The square root of minus 48. By our rule, that's equal to I times the square root of 48. So the question is, can 48 be simplified? Well, 48 is 2 times 24, and 24 is 8 times 3, and 8 is 2 times 4, which is 2 times 2. So this is the same as 2 to the fourth times 3. The square root of 2 to the fourth times 3. So this is an even power. So 2 to the fourth is an even power. So I can bring it out from underneath the radical. And what do? I divide the exponent by 2. So that gives me 4 divided by 2 is 2 squared times I times what's left under the radical, which is 3. But 2 squared is equal to 4, so that's 4I square root of 3. It seems weird. You would actually think you would write it as I times 4 on the square root of 3, or literally 4 times the square root of 3 times I. And indeed, it's just a mess. This is the only part about complex numbers that I don't like. This preference to write it this way is completely arbitrary and inconsistent, because when we write in the standard form, we write it a plus bi, and this would be written as 0 plus 4 on the square root of 3 times I. And there is no other way to write it other than really this last way right here, but many times you will see it written this way. I don't, it's all the same, but it's someone's preference that's got shoved into math that is inconsistent, and I'm not a really big fan of that. So here we have another theorem, and this is an important theorem. So it requires that a and b are greater than 0. And if that's the case, then the square root of the square root of minus a times the square root of minus b, well, from what we previously learned, the square root of minus a is I times the square root of a, and the square root of minus b is I times the square root of b. So I times I is I squared, and the square root of a times the square root of b is the square root of ab, but I squared is equal to minus 1. So literally, again, all of this stuff in the middle here is just my justification. We can start, if we're given this, I'll use the mouse, I have better control. If we're given this over here, we can immediately go to this over here. Okay. So let's do example 2, exercise A. And we have 2a, the square root of minus 7 times the square root of minus 7. Well, from my theorem, I get that is the same as minus the square root of 7 times 7. So remember, we had the theorem, the square root of minus a times the square root of minus b, where a and b are both greater than 0, is equal to minus the square root of a times b. But in this case, a is equal to b, which is equal to 7. So we can simplify this. So coming down here to simplify it, it's going to be equal to minus the square root. 7 times 7 is 7 squared. So it's going to be equal to minus 7. So the square root of 7 squared, because that's an even number, I can remove this out from underneath the radical. The price I pay is I have to divide the exponent by 2. And that's our final answer. Now b looks a lot harder than it really is. Because remember, when you divide something, you're really just multiplying. So let's rewrite the numerator as I times the square root of 20 using our previous. And this is I times the square root of 2. So those i's, actually I divided by I cancels out. So this just turns out to be the square root of 20 divided by the square root of 2. And if you remember your radical rules, if not, you need to go back and review them. That's the same thing as the square root of 20 divided by 2, which is equal to the square root of 10. And since 10 is equal to 2 times 5, there are no factors that are raised to an even power, so that's as far as we can go. So notice I didn't use the theorem I just talked about. I literally used the theorem on our first page. In 2c, right here, 2c, square root of minus 48 divided by the square root of 24. Again, let's work on the numerator. That's just I times the square root of 48 times the square root of 24. But since the square root of 48 and the square root of 24, 48 and 24 are just real numbers, this is the same as I times the square root, using again a rule of radicals that we learned in intermediate algebra. So that's just equal to I, and the square root of 48 divided by 24 is 2. So our answer is just I on the square root of 2. So now for example 3, we want to write this in standard form, which is a plus bi. So the first thing we're going to do is I'm just going to remind you really the rule that a plus b divided by c is equal to a divided by c plus b divided by c. That rule is the rule for real numbers, where a, b, and c are real numbers and c is not equal to 0. It also extends for complex numbers. So a plus bi divided by c is equal to a divided by c plus bi divided by c. So we're going to use that rule to simplify this. So we have minus 8 plus the square root of minus 128 over 4. So the first thing I'm going to do is I'm going to rewrite the numerator. That's minus 8, and it's the very first rule, times I times the square root of 128 divided by 4. And now I'm going to use this rule down here. That's minus 8 over 4 plus I times the square root of 128. Sorry, that's 128 divided by 4. Well, minus 8 divided by 4 is minus 2. And what is 128? 128 can be divided by an awful lot of 2's. So that's going to be 2, 64, 2, 32, 2, 16, 2, 8, I'm going to run out of room, 2, 4, 2, 2. So 128 is 1, 2, 3, 4, 5, 6, 7 is 2 to the 7th power. So that's I times the square root of 2 to the 7th power over 4. I just want a little bit more room here. So again, we're right here. So let's rewrite this. So the minus 2 doesn't change. The real part of the complex number, I figured it out. But now you have to remember how to treat this numerator. So 2 to the 7th is the same as 2 to the 6th times 2. And all of this is divided by 4. So that's equal to minus 2 plus I. Now 2 to the 6th is an even number, so since this is the square root, I can remove the 2 to the 6th out from underneath of the radical sign. What's the price I pay? I have to divide 6, the exponent 6 divided by 2. And what stays underneath is just the square root of 2. We're going to get another simplification here. So that's equal to minus 2. And 2 raised to the 6 divided by 2 is 2 raised to the 3rd. And 2 raised to the 3rd is 2, 4, 8. So that's 8i times the square root of 2 divided by 4. So finally we're going to get minus 2 plus 8 divided by 4 is 2i on the square root of 2. And that's a perfectly fine way to write it. It is right there. Okay. So our next example, we get to add and subtract complex numbers. So this is our second objective, is just adding and subtracting complex numbers, and also multiplying and dividing. Dividing looks really bad, but it's not. It's kind of similar to rationalizing denominators, if you have a denominator that's a radical. So let's bring up this and go to the next. So really, I give you the rule here, and in this case the rules always look much more complicated than they really are. So basically, when we add and subtract complex numbers, we just add the real parts and subtract the imaginary parts. That's all we do. We kind of treat the I like it were a variable x, and we collect like terms and simplify. So adding and subtracting is not hard. Let's go ahead and do these two examples. You know, I say it's not hard, but of course it's not hard for me. 3 minus 4i plus 2 plus 6i. So since this is a plus right here, I can just remove the parentheses. It's understood that this is a plus over here on the left-hand side. So again, we collect like terms. So the 3 and the 2 are pure real numbers, and the minus 4i and the plus 6i are called pure imaginary numbers. all of it together is a complex number. So 3 plus 4 is 7, minus 4 plus 6i is plus 2i. Okay. How come I added 3 plus 4? That's wrong. Sorry, people. It's Saturday. That should be 3 plus 2. So the end result is 5 plus. I even did worse, people. So just forgive me. Notice what I have here is correct if this is what the problem gave us. But that's not what the problem gave us. So let's actually do what the problem gave us. Maybe I should have had some coffee before this. And for those of you who had me before, you know that I do this. 3 minus 4i. This is, I copied the problem down wrong is what I did, and I didn't catch it. Minus 2 plus 6i. The procedure is exactly the same. So we're going to add the real parts and then the imaginary parts. And 3 minus 2 is 1, and minus 4i plus 6i is plus 2i. So that's the actual answer to the problem that was given, and this is the answer to this similar problem that I wrote down differently from what was given. So let's do number 4b. So I have minus 4 plus 3i minus, now minus sign is going to change things. So again, if you have a complex number in parentheses, if it doesn't have a sign in front of the parentheses, you can just remove those parentheses and it doesn't change anything. But this set of parentheses does have a sign. So literally I'm going to distribute minus 6, so minus in parentheses 6 minus 7i is the same as minus 1 times 6 minus 7i. And the properties of distribution hold. In other words, I'm just going to multiply each of these terms by a minus. So minus by minus 1. Minus 1 times 6 is minus 6. And minus 1 times minus 7i is plus 7i. So again, now I just collect like terms. So the pure real terms I collect, and then the pure imaginary terms I collect, and I simplify. Minus 4 minus 6 is minus 10. 3i plus 7i is 10i. So there we go. So not too bad. Adding and subtracting. So literally, when we multiply two complex numbers, we multiply them just like we're multiplying two binomials. We just use distribution, and we just remember that I squared is equal to minus 1. And here literally is a formula. If you want to start out with this, and you somehow want to memorize this, more power to you. I'm not going to do it that way. We're going to go ahead and just multiply it out just like we were expanding the product of two binomials. Remembering that one term is going to have I squared, and I'm going to have to simplify that to minus 1. So there's a lot of different ways, and I'll use FOIL. This is 5a. So we have 2 minus 3i times 3 plus 4i. I'm going to do this two different ways. I'm kind of myself, there's the FOIL method, first, outer, inner, last. We'll do that first. So the product of the first terms is 2 and 3, so that's going to give me 6. Then the outer terms is 2 times 4i. So 2 times 4i is 8i. The inner terms is minus 3i times 3, that's minus 9i. And then the last terms is minus 3i times 4i, that's minus 12i squared. So go ahead, that's 6, and 8i plus 9i is 17i. But minus 12 times I squared is the same as minus 12 times minus 1. So this becomes plus 12. So my end result is 18 plus 17i. Sorry. Yeah, 18 plus 17i. Let me check this. 2 times 3 is 6. We'll just check it by doing it my other way. The reason I'm checking it, I don't see anything wrong here, but I am tired. That's 6 times 3. I just have something written down in my notes. Did I write it down right? Minus 3 times 4 is minus 12i squared. That becomes 12. Yeah, I think it's right. I just think my notes is, I have it written down wrong in my notes. But let's just check it this way. So the other way I like to do this is 2 minus 3i times 3 plus 4i. I like to do it this way. So what I do is I keep this as one thing to itself. So I multiply 2 times 3 plus 4i. And then I multiply minus 3i times 3 plus 4i. And we'll see if I got the right thing. 2 times 3 is 6. 2 times 4i is 8i. Minus 3i times 3 is minus 9i. And minus 3i times 4i is minus 12i squared. It's exactly the same. That's going to be 6. Oh, that was the problem. Minus I plus 12. So it's 18 minus I. Yeah, that was the problem right there. So we discovered it, and that should be 18 minus I. And what I have written in the notes is indeed correct. Sorry about that. I didn't see that. I wasn't paying attention to the negative. So let's go on and let's look at number B. So 5B is 4 plus 3i squared. Remember, that's just shorthand is 4 plus 3i times 4 plus 3i. But I'm going to give you a formula that's really kind of nice. If we have a plus bi, well, I was going to give you the formula that's a squared plus 2abi plus bi squared. That's using special products. So that's a squared plus 2abi minus b squared. So I don't know if this formula is helpful or not. I normally don't use it. Let's go ahead and just do it the normal way. We can FOIL it or do the other way. So 4 plus 3i times 4 plus 3i. So my first terms is 4 times 4, that gives me 16. My outer terms is 4 times 3i, so that's 12i. My inner terms is 3i times 4, so that's another 12i. And my last terms is 3i times 3i, that's plus 9 times I squared. So this is equal to 16 plus 24i, but 9 times I squared is minus 9. And you will see that's exactly what we would have got. So my A is 4, and 2 times 4 times 3, because that's my B value, minus 3 squared is equal to 16, that's an I there, plus 4 times 3 is 12, and 12 times 2 is 24, minus 9. So we get the same. So you can use that special product if you want, or you can just do it this way, or again you could use the other way, and I'm not going to do the whole thing, but the other way, I tend to actually like this. And the reason I like this is because it's used in I just took my last graduate class was a class on algebraic geometry, and we had something called K-linear combinations. And it's very similar to this right here, doing things like this, except we had a lot more terms. And if you do it this way, you'll get the exact same answer. And I am going to give you a formula for C, but I won't give you the formula right at this moment. We're going to discover something about C. So if we look at number 5C, we have 6 plus 5i times 6 minus 5i. Now notice that the real part is the same, and the imaginary part, they just differ in sign. These are called complex conjugates, and if you knew the formula, you can literally write down the answer. It's 36 plus 25. So we're actually going to see that we're going to get that same number, but this is using a formula that I've not given you before, but how nice it was. What is 36? Well, it's 6 squared plus 5 squared is what it is. So let's just do it the normal way. We'll FOIL it. 6 times 6 is 36. 6 times minus 5i is minus 30i. 5i times 6 is plus 30i. Those two just canceled out. And 5i times minus 5i is minus 25i squared. So these two middle terms, the 30i and the minus 30i, they cancel each other. When I add them, they go to 0. So I have 36, and minus 25 times I squared is minus 25 times minus 1, which is plus 25. And 36 plus 25 is 61. So that's a really special and interesting case, something that you'll have to memorize. So, and here's the formula. So these are called complex conjugates. So if you're given a complex number, a plus bi, we form its conjugate by changing just the sign of the imaginary part. The conjugate of a plus bi is a minus bi, and the conjugate of a minus bi is a plus bi. Note that the sign of the real part a does not affect conjugation, as the conjugate of minus a plus bi is just minus a minus bi. And we just discovered and by that quick example, that the product of a complex number and its conjugate, a plus bi times a minus bi, is equal to a squared plus b squared. So this is a really important formula you want to memorize. It only works if you actually have two complex numbers which are being multiplied together, which are conjugates of each other. So remember, the a values have to be identical, and the imaginary value or part has to differ in sign. If this was a plus bi times minus a minus bi, then the formula wouldn't work. So we're going to use a process similar to rationalization of denominators to divide complex numbers. And here I go through a bunch of algebraic manipulation, and it just looks terrible. So it looks way more complicated than it is. So let's just do some examples. So the examples, I'm on example number 6. I won't be able to see that in just a second. So this is example number 6. So we're going to divide. So division is like, how on earth do I divide? So I just said that was 6a, right? Yeah, 6a. So I have 3 plus 2i times 5 minus I. So I want to write this as a plus bi. So that's my goal, is right here. And 3 plus 2i divided by 5 minus I has to equal this. So whatever I do has to be something that keeps the equality. And that trick is going to be, I'm going to multiply this complex number here by a form of 1. And 1 is going to be in the form of a fraction whose denominator is the same as the numerator. So what do I choose? I find the denominator first. What is my denominator? Well, I look at the denominator of my original fraction and I write down its conjugate. So remember, the a values stay identical, but I change the value, the sign, in front of the I. And now once I've discovered the denominator, the numerator is identical. So this is, we're going to multiply numerator by numerator, 3 plus 2i, because remember, multiplication of fractions, that's the easy one, right? And then I'm multiplying the denominators. So the denominators are complex conjugates, so it's super simple. Notice 5 plus I is the same as 5 plus 1 times I. So a plus bi is, a is 5 and b is 1. So this is equal to 5 squared plus 1 squared. Super simple. So over here I just have to, at the top, multiply out using distribution or FOIL these two complex numbers, and I'm going to use FOIL. So 3 times 5 is 15. 3 times I is plus 3i. 2i times 5 is 10i. And 2i times I is 2 times I squared, which is 2 times minus 1, which is minus 2. So now I'm going to go ahead and I'm going to simplify. The denominator is 5 squared plus 1, which is 25 plus 1. 15 minus 2 is 13. And 3i plus 10i is plus 13i. So I've done everything I can do with the numerator. And now let's simplify the denominator. That's 26. And I don't know if that's where my math lab is going to allow you to stop, but we did say we wanted it in the form of a plus bi. So I'm going to use that trick. A plus bi divided by c is equal to a divided by c plus bi divided by c. So this is equal to 13 divided by 26 plus 13i. Seriously, Kent? This is what happens. I didn't get to sleep last night until 2:30. I should have known better. There we go. But now these fractions can be reduced. 13 divided by 26 is 1/2. And this is 1/2 times I. So I feel pretty certain that this is the final answer that my math lab wants. Just to show you that I could actually simplify it further as 1/2 times 1 plus I. I kind of like this better, but I think my math lab is going to basically be okay with that. In other words, what I did is I factored out the greatest common factor of these two terms, which is 1/2. Oh, we have one more to do. Okay, 3 divided by I. Not so bad. In this case, we can literally go through the processes before, but it's really rather redundant. In this case, I'm going to take a shortcut, but I am going to pose the question because you might see it. This is number 6, number 6b. So it's 3 divided by I. So here I'm going to pose the question. Find the complex conjugate of I. Well, the first way to do it is to write it in the standard form. I is equal to 0 plus I. So now I have it in the standard form, so the conjugate of I, which we often denote by a bar, you don't have to know that, would be equal to 0 minus I. So the conjugate of I is minus I. But in this case, I don't even have to do that, because all I want to do is I want to transform it by multiplying by a value of I. A value of 1. So I divided by I is 1. So 3 times I is 3i, and I times I is I squared. So that's equal to 3i, and I squared is minus 1, so that's equal to minus 3i. And we would have gotten the exact same answer had I multiplied it by minus I over minus I using the general rule. It would have been exactly the same. So simplifying powers of I. So actually, especially now that you're in college algebra, mathematics is really not about solving equations. It's about proving things. Some of you are really good at solving equations and symbolic manipulation, but that's really not what math is about. Math is about proving things, and when we prove things, we state the proof usually in the form of a theorem. So theorems are to mathematics like theories are to science, except a theorem in mathematics is much stronger. If the conditions of the theorem are true, then the conclusion of the theorem must be true. There is no possibility for it to be false. So in this case, I give you a theorem, and that theorem just states I cubed is equal to minus I. So let's actually prove this theorem. So what I want to do is I want to start out with I cubed, and then I want to use properties of exponentiation to conclude that it's minus I. So I start with what I'm given, and my bottom line should be I cubed is equal to, the bottom line would be minus I. So I cubed is equal to I squared times I. It's just because I is raised to the first. But I squared is equal to minus 1, and that's times I. So that's just equal to minus I. Could there be an easier theorem to prove? So that's my theorem. I cubed is equal to minus I. And I'm just going to give you a definition. I to the 0th power is going to be equal to 1. I'm just going to define it that way. So now we actually have a pattern. Let's look at that pattern. Let's start out. I to the 0th power is equal to 1 by definition. I squared is equal to minus 1, also by definition. I cubed, by the previous two definitions, or just by the definition of I squared, is equal to minus I. So I to the 4th, let's figure out what I to the 4th is. Well, I to the 4th is I squared, which is equal to minus 1 is I squared, and minus 1 squared is minus 1 times minus 1, which is equal to 1. So I to the 4th is equal to I to the 0th. So it turns out that the pattern repeats itself. This pattern right here is going to be used to solve the powers of I problem. So what you have to do is basically find, when you're given a power of I, find what its remainder is divided by 4. And then use this table right here, or the table that's written down in your notes, to proceed. So we'll do this one. So just remember, I to the 4th is equal to I to the 0th. So this is 7a. I to the 15th. Well, 4 divided by 15 is equal to 3, 12, and I have a remainder of 3. So in other words, 15 is equal to 4 times 3, which is 12, plus 3. So all I care about is the remainder. So that's the same as I to the 3rd, which is equal to minus I. So let's actually, I want to show you that. I kind of did some math magic there. I want to show you the full what went on mathematically. So basically, it's this. I to the 15th is equal to I to the 4 to the 3rd plus 3. Why? Because 4 times 3 is 12, plus 3 is 15. So I just wrote 15 as 4 times 3. Well, that's the same as I to the 4 times 3 times I cubed. But that's the same as I to the 4th raised to the 3rd times I cubed. But I to the 4th is equal to 1, and 1 cubed is just 1. So the answer is I cubed. So that's what actually allowed myself to go ahead and write that as equivalent to I cubed, which we can simplify further as minus I. And one other example, I think, is that it for this particular section, is you're given a power, a negative power of, I have one more question after this, but it's a thought question. You're given a negative power. So here's what I don't want you to do. I don't want you to write I to the minus 3 is equal to 1 over I to the 3rd. You could do it that way, but it's going to be a lot easier if you do it this way. I to the minus 3 times 1 is identically I to the minus 3. But what happens if I write 1 is I to the 4th? Now I can just use the addition of exponent rules. That's minus 3 plus 4. So that's equal to I to the 1st power, which is just equal to I. So what you want to do here is when you have I to a negative number, I'm just going to make up another example. Just one I'm making up. Suppose I have I to the minus 14. So what I want to do is multiply that times some power of I that is evenly divisible by 4 that is greater than 14. And you want to find the one closest to 14 that you can. And well, 16 is evenly divisible by 4, so I to the 16th is still just 1. So that's the same as I to the minus 14 plus 16, which is equal to I minus 14 plus 16 is squared, which is equal to minus 1. Okay, one last final question. Conceptually, it's important. I don't know if it'll appear on your first exam or not. So which of the following statements are true and why? Every real number is a complex number, or every complex number is a real number. So think about that, and you might see it again on an exam. And if you're worried about that, you can always email me your answer and the reasoning behind your answer, and I'll let you know if you're right or wrong. And if you're wrong, I will point you in the right direction. Sorry about the confusion and the mathematical mistakes earlier. It happens, and for the rest of the class, you'll see it again for sure. I am not a genius. I'm just a person who loves math and have studied it forever. If you have questions about any of this, go ahead and hit me up in Teams or send me an email.